Hello, my name is Fikar, and I would like to present you our paper on simple tuning of arbitrary controllers using governors. This was done together with my colleagues Karol Kiš and Martin Klaučo at Slovak University in Technology in Bratislava and Martin Mönnigmann from Ruhr University at Bochum in Germany at the IFAC World Congress in Yokohama. My presentation consists of 4 parts. I will start with motivation and main idea, and then I will show you selected case studies, and I will end up with conclusions. So for the motivation, this paper is, or this presentation is about tuning of the closed loop system, tuning of controllers. And this can be in general done in 2 ways, either offline or online. Usually all controllers can be tuned offline during the design phase. Some of them can be also tuned online, some of them cannot. For example, explicit MPC controller cannot be tuned online or with quite a lot of difficulties. So main tuning goals of my presentation or of this approach is to have a system that makes possible to change the speed of the closed loop system, so make it slower or faster, and also to keep all other properties of the closed loop system unchanged, for example, integration properties, constraints handling, and so on. So the proposed method has 3 tuning properties. One is that it is intuitive. We only use one unique single parameter to change the speed. Then it is applicable to any controller, even if we don't know this controller, even if it is embedded or anything. And the third one, it's non-invasive. It means that all other controller properties should stay. So integral action or constraint satisfaction should stay. So what is the main idea of this approach? It's quite simple. We will use the so-called governor. So it's an additional term in the closed loop system which we place in front of the controller, so at the controller input, and the governor will send modified reference and modified output to the controller. For example, with a tracking error, if there is only one parameter to the control tracking error, then we have this gain k that scales the tracking error and sends to the controller modified tracking error. So if it is equal to 1, then nothing changes. It's the nominal closed loop system. If it is greater than 1, then the controller thinks that the tracking error is larger than it is actually, and that's why its actions will be more pronounced. And if it is less than 1, then it will be more cautious controller, because it will think that the tracking error is actually very small. We can have several possible configurations. So I already spoke about the error governor, but we can have, for example, in the case of state feedback control, we can use state governor, where we multiply all the states by this constant gain, or reference governor, which is that we will keep the process output unchanged, but based on the relation between modified tracking error and the original tracking error, we can calculate the modified reference value, which is a linear combination of the original reference and the original process output. And in the same way, we can, for example, do output governor, even we do not have a very good experience with this one. So, for example, with reference governor, what happens if there is a step change, which is this green line? Well, if we want some slower closed loop system, then we will send slower slower reference change, you can see that it asymptotically goes towards the green line. And if we put the weight greater than 1, then the controller sees the set point, which is actually larger than the nominal 1. And it changes, the controller changes its action accordingly, so the very cautious red one and very active blue one, and the nominal one, the green one, is between them. And you can also see nicely what happens with the controlled output, that we can shape, we can do underdamped, overdamped process response. So for the case studies, I will start with explicit MPC. And as I said before, explicit MPC is a kind of controller that you have to design, and it will take quite a lot of time to be designed. But when it is done, it's very fast to execute. But on the other hand, it's impossible to change. So you have to repeat the whole procedure again. So if we, for example, take a double integrator, discrete double integrator with input constraints and with state constraints, and let's define the weights, which will be quadratic cost function, then for this scenario we'll calculate explicit MPC, which is defined over 33 state space regions. And instead of recalculating for different weights, we can use the state governor, so only one parameter will change. And if you see here the state portrait with variables first and second state, and we start with the point 1 minus 1 and we go to the origin 0, 0. You can see, for example, this magenta line that it goes quite slow, or the blue line or yellow line that go very, very quickly. And with the slow one, we can see that the manipulated variable even doesn't hit the maximum 0.5 constraint, but all others, they will hit it. So we can effectively change the speed of the closed loop system with explicit MPC controller, and we still have the constraint guarantee. If we show also the domain of the explicit MPC controller with this blue line, then we can see that we are very safely within this domain. There is quite a lot of space, so even if we scale these states, we will still be within this domain. But the situation can be different if we are closer to the border of this domain. So if we will scale these states, for example, by 2, then of course we will get somewhere here, and it will be outside of the domain, and there will be no controller that can be calculated. So how is this done for such a scenario? We will use time varying governor. So these values of gains are actually the maximum value can be attained, and you can see that at all cases in the first 8 steps, we follow the same trajectory of states, and only afterwards, if we are closer to the origin, there will be some distinction between those trajectories. So what happens here? If we show the scaled states, so multiplied by the value of the gain, and if we show the time evolution of the gains, so the red one is the nominal one that doesn't hit the constraints at all, and for example the green one, we can see that we cannot be always at a value of 1.4, but we have to find such a value of the gain in each step so that the scaled states remain within the domain. And this is a very simple optimization problem that can be solved within several iterations using, for example, bisection, where we find if we are in the domain with the value of this parameter k. And the second example is again a controller that cannot be tuned online. It's a neural network MPC approximation. So we will assume that we have a multivariable process with 2 inputs and 2 outputs. We will design MPC controller, which is quite complicated in this case, more than several thousands of regions. So we will learn neural network controller based on this optimal controller. And of course, it takes quite a lot of time and effort to have this neural network controller. And once it is calculated, it's very difficult to change. We have to repeat the procedure again. Instead, we will use the setpoint governor. You can again see here are the outputs of the process, the temperature and height. And the nominal one is the green one. And we can effectively change the speed of both outputs. They still are within the constraints. And also the two manipulated inputs, the valve openings. We can see that we can easily go between cautious control and more active controller. There are also, in the paper, you can find more examples, for example, constrained PI control or multivariable decoupling control, but I will skip those due to lack of time. You can read it in the paper. So I will come to conclusions. So what we propose is a very simple structure of a governor used for controller tuning. It has only one parameter, so it can be easily tuned. There are no procedures what should be the value of the gain. Instead, we propose to do is heuristically to increase or decrease it by certain amount and see how this work. We have very good results with a reference governor. And of course, stability, we didn't speak here about stability, but stability can be determined, for example, using root locus procedures or using robust control methods. We show, for example, here the approach for explicit MPC with time-varying governor gain. If you want to see even more, you can see the technical report, which is on our web page. And also the second reference is on application of drone control with cooperation with German colleagues. We have neither real-time or experimental results. So with that, I would like to thank for your attention, and maybe you can write me if you have any questions or comments. Thank you.